Hey guys, the last time we talked about 4.3, we talked about the derivative of exponential functions. So for example, the derivative of e to the x would be e to the x itself, right? This one is the symbol for derivative prime. Another scenario is that, say, if I'm asking you to take the derivative of 2 times e to the, 4x plus 3 in here. If you notice, the power in this case is not x anymore, it's like another function, right? So that means we have to take the chain rule, or we have to take the derivative of this new exponent or this new power, and then we multiply it with the derivative that we have. Okay, or if you want, you can refer back to the inside-outside table that we learned about the chain rule in the past section. Okay, so then the derivative of 2 to the something will be just itself. So then I'm gonna go ahead and copy and paste the whole function down. So 2 times e to the 4x plus 3, and then on top of that, I'm going to multiply it by the chain rule, which is the derivative of the power, which is 4. So then my final answer for this one would be 8 e to the 4x plus 3. Okay? And just really quick about like a summary of what we have been learning so far. These are all the rules that we learned in order for us to take the derivative in a faster way. So make sure you have all these down. And the most important one in here is the chain rule. As you can see, it's really important. We already experienced in the quizzes and the tests. Make sure you know how to apply it on the derivative, okay? And then before we jump into the first objective of the day, let's remind us about the 5 properties that we learned about logarithmic functions. So we know that ln of e is 1 by definition. And same thing, log of 10 is also equals to 1, right? This is the natural log function, and this is the common log function. Okay, so this is my natural log function and common log function if you want to recall them really quick. So in here, ln of e to the x is x. How come? Well, first of all, we know that the x in here is the power, so we're going to bring the x on the outside, so it looks like x times ln e, and then ln e in here is just 1, so then we end up having x. Okay, this is the sum and this is the difference, so make sure you remember how to apply it. We already had it in the exam one, but make sure you know how to do it because you're going to see it again in the final. Okay, and this one in here, you barely see it, but technically we're switching the role of e and x in here, so you can think of it like from here we had e to the ln x equals to x to the ln e. Okay, and then again ln e is 1, so then it means that we have x to the first power, which is x. Okay, the last one, this one is the most commonly used. Whenever we have a power, we have to bring it on the front, like out to the front, right? So in here, n is the power, so then the answer for ln of x to the n power would be just n times ln of x. Okay, and let's talk about the first objective of today: derivatives of logarithmic functions. Okay, so if you remember, the inverse of exponential function is actually logarithmic function, right? That's why we're doing it back to back. On 4.3, we'll talk about the derivative of exponential, and then on 4.5, we're going to talk about the derivative of logarithmic functions. So the very first note in here, implicit differentiation can be used to develop the derivative of natural logarithmic function. What do I mean by this? Remember that way before we talked about the set of rules to help us find the derivative, we also talked about the definition of derivative, right? Which is by using the limit of the quotient like formula, and from there we have to do a lot of algebra, and then at the end we plug in 0 for h or 0 for delta x, if you remember it. So that's like one way to help us develop the formula for the derivative of log, but for the sake of time and for the sake of the simplicity, let's not talk about like all the derivation of that. Okay, so basically to find the derivative of ln x, we can rewrite the logarithmic function to an exponential function, which we already know how to take the derivative of. Okay, so originally we're going to start with the function y equals to ln x. So this is the logarithmic function that we want to take the derivative of, right? But then we don't know how to take the derivative of that because we don't have any formula yet. So then we're gonna go ahead and rewrite as the exponential function. So it looks like x equals to e to the y power. How come it looks like that? Well, if you remember the circle thingy, let me write in here then. So we have ln is log base e, right? And then this is x, and then equals to y, right? So we have e to the y power equals to x, which is what we have in the pink highlight in here. Okay, and if we take the derivative of both sides in here, for derivative of x, we're gonna have 1 because x is like x to the first power, right? And then the derivative of x is 1. The derivative of e to the y power would be just itself, but then we have to multiply by the chain rule in here, which is dy dx. So let me just point this out really quick. This part we have is due to the chain rule. And this part in here, e to the x, we have it because we take in the derivative of e to the x. Okay? And eventually, remember that e to the y power is the same thing as x in the pink highlight. So let me take these errors out. So e to the y power is the same thing as x. So then we're gonna go ahead and replace e to the y power by x. Okay, so eventually we have 1 equals to x times dy dx. Okay, and then we're gonna go ahead and solve for dy dx in here. We're gonna go ahead and divide both sides by x. So then we will have dy dx, or the derivative of y equals to 1 over x. So to summarize all of that, the formula in here is the derivative of ln x equals to dy over dx, or should I say 1 over x. Okay? So summary. Whenever you have to take the derivative of ln function, make sure you put 1 over whatever inside of the ln function, okay? So chain rule in here would be applied if you have like another function rather than x on the inside. So if you notice, whatever you have inside the ln, when you take the derivative, it would be like 1 over it, and then we have to multiply it by the chain rule, okay? So to make it more clear, let's talk about the first example in here. So on my side, I'm gonna go ahead and take the derivative of this function, ln of this fraction. So f prime equals to, what do I do? So if you notice, on the inside of the ln, we have the fraction of x squared plus 1 over square root of x, right? So I'm gonna go ahead and put all that underneath of 1. Okay. And after that, I'm gonna multiply it by the chain rule because, okay, let me help you guys by this. So this part is this part on the formula, okay? And then now we're gonna talk about the chain rule. So then the chain rule in here, we have to take the derivative of x squared plus 1 over square root of x. And this one in short is the quotient rule, right? So then we're gonna have like f equals to x squared plus 1, and then g equals to square root of x, or x to the like 1/2 power, right? Let me put it in that way so that it's easier for me to take the derivative of it. So then f prime in here, it equals to 2x, and then g prime in here, it equals to 1 divided by 2 square root of x, in short. Okay, and then the chain rule in here applies. How do I apply that? So let me go ahead and copy this one further down here. Okay, so now this equals to what? We're gonna have f prime times g, which is 2x times x to the 1/2. So if you remember, x times x to the 1/2, in here we don't have the power for the x, so we're gonna put like a 1 in there. So then we're gonna add up all the powers together to get 3/2 in here, which is that. And then for the outer cross, we're gonna have minus, because we're talking about the chain rule, because we're talking about the quotient rule. And then we multiply f with g prime to get x squared plus 1 divided by 2 square root of x. And all of that is over square root of x squared for g prime. I mean for g squared. Okay? So let me go ahead and get rid of all of this outside work for the quotient rule. And let's simplify this ugly like expression in here. So right off the bat, I can cancel the square with the square, and then after that I'm gonna multiply everything of the first fraction by 2 square root of x to get a common denominator. So it looks like 2x to the 3/2 times 2 square root of x minus x squared minus 1. Okay, let me put this minus in another color because a lot of people, they mistaken it by a plus. How come we have the minus in here? Because remember, the minus in here is for the x squared and also for the 1, right? So make sure for the 1, we also distribute the negative into it. So we're going to have a negative 1 rather than a positive 1 in there. Okay? And we're going to put all of that underneath of x for this x in here, and then times 2 square root of x for this bottom right here. Okay? So then, okay, let me take it outside the graph again. So for this part, let me put it in, I don't know, orange. This part in here, outside work, 2 times 2 is 4. We all know that, right? So that's the easy part. Let's skip that. For the part that has x to the 3/2 times square root of x, we know that is 1/2. So we're gonna go ahead and add the power in here. So then 3/2 plus 1/2, we're gonna get 4/2, which is 2, right? So this turned out to be x squared. Okay, and all of that just to tell us that the thing in the orange circle on the previous line, it equals to 4x squared, and then we have minus x squared minus 1, and on the bottom line we're going to put everything together as 2x squared of x. Okay, and now we're going to go ahead and combine the like terms in here. So in short, this would be 3x squared minus 1 on the top. So let me go ahead and write 3x squared minus 1 in here. So this is for the chain rule, okay? So then let me go ahead and copy and paste that in here as for the chain rule. Okay, that is an ugly writing, so let me go ahead and erase all this before I go ahead and I do that. Okay, that looks better. Okay, let me go ahead and take care of that. Okay, so again, the orange circle in here is for the part that has 1 over u, and then the other one, let me put it in blue, du dx for the chain rule. This is this. Okay? So then how can we simplify it further, right? So first of all, for the first fraction, if we flip it upside down, then the bottom will become the top, and then the top part will become the bottom, right? And then we're gonna go ahead and multiply it by the second fraction. So I'm gonna go ahead and rewrite it. And if you notice, we can cancel out the square root of x in here for both fractions. So putting everything together, we're gonna get 3x squared minus 1 on the top divided by 2x times x squared plus 1 on the bottom. Okay, so usually this is okay. This is good enough for me as a final answer, but if you want, you can also go ahead and distribute the bottom, okay? But then usually, we don't really distribute the bottom at all, like in any problem. So usually we'll just keep it as a final answer. Okay, so the circle one in here is like an outer alternate answer, the final answer that you can get. But the boxing one in here is the one that I really expect you guys to get to, okay? And then let me put a green star in your part, okay? So for your part, a heads up in here is that you have to apply the quotient rule. No, not quotient, product rule, okay? So make sure you apply the product rule for the chain rule, okay? And now let's talk about how to apply it into real application, okay? So then, let's see. For my example, I have the cost of producing X units of a product is modeled by this function, this cost function, and then X has to be greater or equal to 1, and then we have to find the minimum cost. Okay, so by the graph, like obviously the minimum cost in here would be like 31.77, right? But how can we get to that, right? And again, like in the test, never use a graph to, you know, like show me, okay, here's the answer because that's what we get from, you know, like using the graph or like using decimals, okay? Because like the work in there is not our work, it's like the computer work, okay? I want you guys to show some work. And the graphs in here are only for us to check whether our answer is right or wrong. It's not for us to tell the answer, okay? So make sure you don't ever do that on the test by like drawing the graph and then call it the answer, okay? Don't ever do that. Okay, so how do I do that? For minimizing the cost in here, we think about the first derivative, right? So I told you guys in the past already, for optimization problems, whenever we talk about maximizing or minimizing something, we talk about derivative. Okay, so that means that we have to take c prime or the derivative of the cost function. Okay, how do we do that? Well, the derivative of 100 is 0 because 100 is just a constant. Derivative of 25x is just 25, and then the derivative of, I don't see this one. Okay, so this one is like negative 120 ln x. It would be just negative 120 because it's a constant, and then times the derivative of ln x is 1 over x. Okay, so in short, it's gonna look like 25 minus 120 over x. Okay, and how can we find a minimum in here? Well, we're gonna set it equal to 0, and then how we're gonna solve for x. Okay, so in short, if you were to do it correctly, you're gonna get 120 divided by x equals to 25, which means that x equals to, what is it? Calculator. 120 divided by 25, 4.8. I mean, if you were to do it correctly, well, the x coordinate will be right here for us to check, right? So this is like the amount of unit we gonna get for the minimum cost, right? But then they're asking for the cost, not the unit. So that means that we have to plug it into the original function right here to get the cost. So it goes like C of 4.8. And by the way, if you want to put the unit in there, it will be like 4.8 units. Okay, equals to 100 plus 25 times 4.8 minus 120 ln of 4.8. And this is an ugly 0, so let me get rid of that. Okay, if you input all that into the calculator, you're gonna get 31.77. Okay. Okay, an iffy thing about this work in here is that how do you know whether this one is the minimum cost or the maximum cost, right? Because this in here is the critical number, and we all know that critical number can create a minimum or a maximum or neither, right? So how can we confirm that this is indeed a minimum, like a relative minimum, right? So in the test, make sure you do the following work to confirm with me that we're producing the minimum cost. Okay, so then we learned about the second derivative already, so that means that we have to take the second derivative of this. So second derivative of the cost function, it equals to what? 25 will become 0, and then the negative 120 divided by x, the derivative of it would be 120 divided by x squared, right, in short. And if you don't know how to do that, well, here, let me do it slowly. 25 becomes 0, so we're gonna like slash it out if you want. And then this one, it becomes negative 120 x to the negative 1, and then the derivative of it will become negative times negative 1, which is a positive 1, and then we have 120 x to the negative second power. And then if you rewrite, you're gonna get this, okay? And what do we do after that? Well, we're gonna plug in 4.8 into the second derivative, right? And in here, if you do it correctly, you should get something like 5. Okay, let me move this thing a little bit to the left so that I have more space to write. Okay, so then this one equals to 5.21, which is a positive number, right? Or it means that it concaves upward. And we all know that if the function concaves upward in here, then we're gonna have a minimum. So this confirms with us that we have a minimum indeed, not a maximum or like any other cases. Okay, so make sure you do this little extra work in blue just to confirm that we do produce a minimum. Okay, but the final answer in this work in here in this problem would be 31.77. Okay, and then as for your work, you're gonna have this problem right here in green star. For your work, you have to, they're talking about the rate, right? And also the rate means the derivative, right? So we have to take the derivative of this function, beta in here in Greek letter. But lucky on your side, you don't have to confirm whether it's a max or it's a min, because they don't even ask for max or min, right? They're just asking you for the rate. So whenever you finish taking the first derivative, you set it equal to 0, and then you based on the question in there to find the beta or the I, depending on the question. Okay. So now, well, we confirmed our answer with the graph already, so it's right. So then let's talk about the last objective, outer basis. Okay, so the two special logarithmic functions that we learned so far is the natural log function, which is ln function, and the common log function, which is log like of x, right? Like one is the natural log function is with base e, and then the common log function is the one with base 10. But it doesn't mean that those are the only log functions that we have. We also have like other log functions, right, with different bases. So the common formula in here, the general formula would be this one. Let me highlight it in red. Okay, so a in here is the base. It can be any number that you want it to be, depending on the problem too. So let's talk about the first line here. Recall that the 1-to-1 function y equals to f of x has an inverse function that is defined implicitly by x equal to f of y. So if you know this, we start with this function y equals to f of x, and then we inverse it. So we swapping between x and y position to have x equal to y, f of y, right? And the name of it is the inverse function because they are inverse function of each other in the process of interchanging x and y. Okay. In particular, the exponential function y equals to a to the x power. Let me get rid of the circle. So this one, let me highlight in yellow for the first function. It's a 1-to-1 function, so then it has the inverse function defined implicitly by x equal to a to the y power, right? So let me highlight in blue in here. So again, for inverses, we just interchange the x and y part, right? And this one, the x equal to a to the y power is written implicitly, right? So this is implicitly. Another way to do that is that we can do it explicitly by writing y equals to log base a of x. Okay? Because if you want to think about it, well, let me bring it outside here. So log base a of x equals to y. Well, it comes together in a circle, right? So it goes like a to the y power equals to x, which is exactly the same thing that we had in the blue highlight here. Okay? So there's two ways to write the log function. One of them is by using the exponential function, and the other one is by using the log function. Okay? If a is greater than 0 and a is not 1, then the exponential function with base a is given by the formula f of x equal to a to the x power, where a in here can be any number, okay? But a in here, it has to be greater than 0, okay? So don't give me something like, I don't know, like -2 to the x power. We not talking about this type of function, okay? And we're not going to talk about a function that has space of 1, okay? But a in here, it has to be different than 1, and it has to be a positive number, okay? In terms of logarithmic function to the base a, where a is greater than 0 and a is different than 0, it is defined by the function y equals to log base a of x if and only if this requirement or this formula is satisfying, right? Because if you want to think about it, these are the same thing, right? Like the circle thingy in here that I just did over here, they're the same thing, but it's just like different appearance. The domain of logarithmic function is always, it covers all the x number that is positive or like greater than 0, okay? So inside a log function, you cannot have a negative number and you cannot have 0, okay? So make sure you remember this one because I think I'm going to ask you guys about the domain of log in the test. And you guys have to tell me that the domain of log is everything that is positive and not equal to 0, okay? So in short, to demonstrate that, we cannot have something like log of, I don't know, -2 in here because -2 is not greater than 0. We cannot have ln of 0 because ln is another type of log, and then we cannot have 0 inside ln or log. Okay, so make sure you don't do negative number and make sure you don't do 0 inside a log function, inside any log function. Okay. Lastly, logarithms to the base 10 are called common logarithmics. Most calculators only have 2 logarithm keys. A natural logarithm key denoted by ln is a natural log that we already know, and then a common log key denoted by log. So make sure you can tell the difference between the common log and the natural log, okay? Logarithms to the bases can be evaluated by the following change of base formula. Okay, so this one is a big key point here that we all have to remember, okay? Say if I want you guys to compute, I don't know, like log log base 2 of 3. Well, we cannot do that, right? Because in the calculator, there's no button for us to do 2 and 3 at the same time. So then that's why they came up with this formula, base of change. Okay, so whenever you have like a number for the base and a number for, you know, like the inside log, we're gonna do the base, log of the base divided by log of the inside number. Okay, so there's two options about this one. You can go with the common log, so you can go with the ln log or the natural log, right? Like it doesn't matter, but make sure you don't do a mix and match up natural log and common log. Okay, make sure you don't do things like, I don't know, ln of x divided by log of a. This is weird. Or make sure you don't do things like log of x divided by ln a. This is also weird. Okay, make sure you don't do a mix and match. It just has to be like both ln's or both logs. Okay, so for this example in here, if I want to use a calculator to approximate this log base 2 of 3, I'm gonna go ahead and do log 2 divided by log 3 divided by log 2. So the bigger number goes onto the top and the smaller number goes onto the bottom. And what I mean by bigger and smaller number in here, I'm talking about the size of them, not like about like big and small. Okay, so say if I were to change a problem into, I don't know, let make it like 7 in this case, then the bottom number is going to be 7, because 7 in here is a small in size number, right? Or if I don't want to do it like that, I'm going to do ln of 3 divided by ln of 7. But the key point here is that make sure that the bigger size number goes onto the top, and then the smaller size number, this one, goes onto the bottom for whatever like log you want to use, either common log or natural log. Okay, so this is how you can calculate any of the logs by using the calculator. Okay, talk about derivative in here. We're gonna have like some rules in terms of log or exponential function in general. So then I'm not going to talk about how they came up with these formulas in here, but pretty much you can just memorize it, or if you want, write them down on a piece of paper and make sure to have them ready for the test. But I'm pretty sure I'm not going to test you too much on this one. Okay, if I were to test you, I'm just going to ask you one question at most about other bases of log. Okay, so the derivative of a to the x power is the same thing as a to the x, but then we have to multiply it by a constant, which is ln of a. Okay, I mean, if you want to think about it, well, the derivative of e to the x power is indeed e to the x power, and then multiplied by ln of e, because e in here is the base, but then ln of e is just 1. That's why the derivative of e to the x is just the same thing as e to the x. Okay, but then for other bases, well, ln of 2 is not 1, right? Ln of 3 is not 1, right? That's why we also have to attach that constant of ln of a to the derivative that we're talking about. And then for chain rule in here, make sure you apply the derivative of the function on the inside. Okay? And in terms of log in here, if you remember for the derivative of ln x, for example, we learned that the derivative of ln x equals to 1 over x, right? So same thing happens in here. We're going to have 1 over x. But like to compromise the base in here, because we have the number a, right? And it looks like we haven't used it. Well, we have to multiply by 1 divided by ln a in here. Okay, so my trick to remember it is that for a in here, we have to multiply, and for log in here, we have to divide. Okay? How do I remember which one is multiply and which one is to divide? Well, if you already remember that the derivative of ln of x is 1 over x, then it comes together with the ln a on the bottom because they both are division. And for the other one, it doesn't have any division, so, well, you just have to like go along with it. So let me demonstrate what I just talked about. So this one in here, you have two fractions, and this one has no fraction at all, okay? So if you were to mistake this one by writing like a to the x times 1 over ln of a, you would know that there's something weird, because this one, it doesn't even have like the fraction to multiply with, right? And if you were to mistake this one by writing 1 over x times ln of a, you will know right away, because this one, it doesn't have like the fraction to multiply with it, right? So you have to like switch them around. Okay, so let me get all that out before you get it inside your head. And lastly, let's talk about some example before we get into the real example. So for example, in here, if we were to have log base 2 of 1 over 6, well, first of all, 16 is not like a prime number, so it's a composite number, right? So I'm gonna go ahead and do the tree for 16. So I have like 4 times 4, and each of the 4, I can break them down to 2 times 2. So in total, I have like 4 2s for 16, right? It's meant to be a 4 in here, not a 5. Sorry for that. And because I have like 1 over 16, that's why I have like the negative 4 in here. The negative is for, you know, like flipping, okay? So in order to rewrite, okay, let me just write over here. Alright, actually that's fine too. So then 1 over 16 in here will be replaced by 2 to the negative 4. Okay, so let me change. Okay, so this part in here is replaced by that part. Okay, and eventually we know that by one of the properties from log, whatever we have the power on the inside, we're going to go ahead and bring out the power to the outside, right? So from here, we're going to have negative 4 times log 2 base 2. And then log base 2 of 2 is 1, right? So we end up having negative 4 times 1, which is negative 4. So the answer in here is negative 4. Okay? And similarly, this one is the same example that I showed you guys before. 15 in here is a big number, so we're going to go ahead and write on the top. 2 in here is a smaller size number, so we're going to go ahead and write a 2 on the bottom. You can use ln in here, or you can use logs in here. It really doesn't matter. You should end up having the same answer as 3.91. Okay? So now, let's talk about the real example that we have. Okay, so we have to find the derivative of the function, and in here, if you notice, the base in here is not e or 10 anymore, right? So how can we do that? Well, the derivative of ln, log in general, would be like 1 over the inside, right? So f prime in here, it equals to 1 divided by the inside, which is x squared minus 3x. Okay, and then on top of that, we have to multiply by the chain rule, which is du over the dx that you usually see in the formula. So then the derivative of 2x minus 3, it equals to x squared minus 3x, it equals to 2x minus 3, right? And lastly, because we're talking about log base 3, not log base e or base 10, then we're going to go ahead and multiply it by 1 divided by ln of 3. This 3 coming from the base, so let me write in another color for us to know. So first of all, this in here coming from the derivative of the problem, and green, the 3 in here is, okay, let me just put a 3 in here and then highlight it in green. So this 3 is for like the base 3, okay? And together we're gonna have this equals to what? We're gonna get 2x minus 3 on the top part, and on the bottom we're gonna get ln of 3 first because it's just a number in parentheses, and then x squared minus 3x in parentheses. And this is it. Okay? So there are 3 things about like taking the derivative of logs. First of all, make sure you flip all the way, like whatever on the inside of log, flip it. And then make sure you also take the derivative of the thing that you just flipped. And then lastly, talk about the base in here. Make sure you attach a 1 over ln of the base. Okay? And then just simplify to get the final answer. Okay? And as for your part, let's do this one. Okay? So this is all we have for today. If you have any question, let me know. Email me or text me on GroupMe, okay? Thank you for your listening. Take care and have a great day. Bye-bye.